Hello everyone, my name is Yadan, and today I'm going to present our work, Adversarial Bipartite Graph Learning for Video Domain Adaptation. And this is a joint work with Huang, Zijian, Wang, Mahsa, Baktashmotlagh at the University of Queensland and Zheng at the Harbin Institute of Technology, Shenzhen. So nowadays, with the rapid growth of multimedia streaming and gaming data, understanding human actions and events in videos have become increasingly important, especially for practical tasks like video retrieval, surveillance, and recommendation. So over the past decades, great efforts have been made to boost recognition performance with deep learning for different purposes, such as modeling the appearance and short-term motion, temporal structure modeling, and human skeleton pose embedding. While effective, those deep learning techniques enables machine recognition at a great cost of the labeling large-scale video data. So to relieve the burden of tedious and expensive labeling, one alternative is to transfer the knowledge from the existing labeled training data to unlabeled target test data. Here we call the label-rich domain as the source domain and the label-scarce domain as the target domain. However, the source and target sets are commonly constructed under varying conditions, such as illuminations, camera poses, and backgrounds, thus leading to a huge domain shift. So for instance, in the shown gameplay to kinetics dataset, which is built under the challenging synthetic to real protocol, the training videos are generated by game engines and the test samples are collected from the real scenes. So in this case, the domain discrepancy between the source and target domains inevitably causes a significant drop of the model performance. So to tackle the dilemmas, domain adaptation approaches have been investigated to close the domain gap by either aligning the distributions across domains or learning the domain-invariant representations. While the notion of the domain adaptation have been widely exploited in the past, the resulting technologies are generally designed to cope with still images rather than the videos. So this image-level DA methods could hardly achieve good performance on video recognition tasks, as they do not take into account the temporal dependencies of frames when minimizing the discrepancy between the domains. And early efforts on video domain adaptation utilize a shallow model that applies collective metric factorization, or PCA, to learn a common latent semantic space for the source and target domains. Of late, the focus have shifted to the deep models to address domain shifting in the video using adversarial learning, where the feature generator is trained to fool the domain discriminator so that the features from different domains cannot be discriminated. So in 2018, the Deep Adversarial Action Adaptation Framework was proposed, which termed as a DAA. So it first segments a source and target videos into a set of fixed length action clips, and then extract the clip features with a 3D CNN model. And in this case, it can directly match the video segment representations from different domains. In addition to spatial discrepancy between frame images, videos also suffer from the temporal discrepancy, which can be considered as a local temporal dynamics with different contributions to the overall domain shift. Motivated by this, the TS3N assigns different weights to the source and target segments with a proposed temporal attention mechanism, forcing the model to attain the temporal features of low domain discrepancy. And different from the prior work that mainly concentrates on the intra-domain interactions, TCON proposes a cross-domain coattention module to measure the affinity of the segment pairs from the source and target domains, and further highlight the key segments shared by both domains. However, existing adversarial video domain adaptation methods are limited in three aspects. First, when data distribution embody complex structure like videos, actually there is no guarantee for the two distributions to be sufficiently similar even when the discriminator is fully confused. Second, existing algorithms perform asymmetrically at this training and the test stages. For instance, the TCON takes input the source and target pairs and calculates the cross-domain attention scores at the training stage, but only inference based on the target data at the test time. So this discrepancy inevitably causes exposure bias and hurts the model performance. A third, utilizing a general domain classifier for adversarial learning is only able to match marginal distributions, and so does not align the class conditional distributions. And the video recognition models trained in this manner are less likely to achieve the class-wise alignment. So to address the issues mentioned above, in this paper, we take a more feasible strategy, which is to construct a domain-agnostic video classifier instead of pursuing the domain-invariant feature learning. So in the proposed adversarial bipartite graph, the video classifier is directly exposed to the mixed cross-domain representations, which preserve the temporal correlations between the source and target domains, and modeled with a network topology of the bipartite graph. To model the data affinity across two domains, we naturally formulate the problem with a frame level and the video level bipartite graph, whose nodes can be divided into two disjoint and independent sets, with the edges connecting the nodes from different sets. So the general pipeline can be divided into 4 stages. First, we're mixing the similar source and target features with a frame level bipartite graph, and we aggregate the frame features into the video representation and construct a video level bipartite graph. And then we align the class conditional distributions with adversarial learning. And finally, we classify the obtained source and target video representations. So as the first step, the source and target frames are sampled as heterogeneous nodes so that we can learn the features of edges connecting two types of nodes and measure the affinity among them with edge-opted network. Through message passing, each node will aggregate the features of its heterogeneous neighbors, forcing the features coming from the same class to be mixed evenly in the shared subspace. To group the sampled frames in a unified video representation and capture the appearance and the temporal dynamics, the frame aggregation is applied to the learned source and target node embeddings. So as a proposed framework is agnostic to choices of frame aggregation, we examine multiple aggregation functions, including a symmetric pooling function, which is invariant to the orders of frames, and two memory-based modules to capture the temporal information among the frames, and a temporal relation network to explore multi-scale temporal dynamics. So for difficult tasks, we additionally apply a video level bipartite graph on top of frame aggregation network, fusing the source and target data hierarchically. It allows the video features to be grouped in the tighter clusters, which improves the classification performance. And similarly, we construct a video level directed graph where the features of nodes and the edges are learned through message passing. And besides leveraging graph neural networks to fuse the source and target neighbors, a conditional adversarial module is applied to align the class conditional distributions. To achieve this, the module is composed of a label embedding function, FL, and a domain discriminator, D. And the label embedding function projects the source, video label, and the target predictions from the classifier into latent vectors that's providing domain-invariant semantic cues for the domain classifier D. Then the domain classifier is conditional on the classes for which sample may belong to and trained to discriminate between the features coming from the source or target data. So the bipartite graphs are viewed as a feature generator to fool the discriminator. And lastly, the proposed model is trained in a min-max manner. So along with the graph neural networks, the classifier is trained to maximize the domain loss to close the domain gap while minimizing the LYS, the cross-entropy loss of the labeled source data, and LYT, the software entropy loss for unlabeled target data, which alleviates uncertainty of predictions. To verify the robustness of the proposed ABG and HABG structure, we further extend them to a semi-supervised setting. So in this circumstance, part of the target labels are observable for training, and we derive the additional edge supervision losses. To verify the effectiveness, we compare and construct our proposed approach with the existing domain adaptation approaches on 3 benchmark datasets and 1 challenging connected to gameplay dataset. For fair comparison, we follow the dataset partition and the feature extraction strategies from the previous works that utilize the ResNet 101 pre-trained on the ImageNet and as a frame-level feature extractor. With different backbone networks, the comparison results achieved from the relatively small datasets are reported in Table 2, and the source only indicates the backbone model pre-trained on the source domain and tested on the target domain. We can find that the deep video dataset DA methods generally outperform the non-deep DA methods and the classification models without DA. So with the same backbone of TA3N, our ABG model performs comparably without relying on the frame attention or complex frame aggregation strategies. The phenomenon is also observed in the large UCF to HMDB4 dataset, in which the proposed ABG with average polling boosts the performance by up to 11%. And here, target only denotes a backbone model trained or tested on the target domain, which serves as a super baseline. In general, the proposed ABG framework is superior to the compared image level and video level domain adaptation methods in most cases, especially achieving a great significant performance boost on the large-scale testbed. And to study the robustness of the derived algorithm, we extend the unsupervised domain adaptation to a semi-supervised setting and conduct extensive experiments on the most challenging kinetic to gameplay dataset, on which the results with varying ratios of target labels are reported. And the proposed semi-ABG and its hierarchical version, the semi-HABG, achieve higher recognition accuracy on both two transfer tasks, since the integrated graph help to propagate the label information and take a full advantage of the supervision. To investigate the validity of the derived module and objective functions, we compare the 4 variants of ABG models on the full UCF to HMDB dataset. So removing the bipartite graph, the ABG without graph suffer a drop dramatically compared with the full model. The ABG without LD is a variant without conditional adversarial learning, and the ABG without LYT refers to the variant without entropy loss for target data, which triggers a slight decrease on the model performance. And here, HABG is a variant. Is a hierarchical variant of a plain ABG model, performing better on the challenging HMDB to UCF full task, which is consistent with the findings in semi-supervised experiments. And to study the effect of the loss coefficients, we conducted the experiments with varying values of loss coefficients beta and gamma, which balance adversarial loss and entropy loss respectively. As plotted in this figure, the average accuracy for both ABG and HABG model becomes quite stable when reaching sufficiently large loss coefficients. And this indicates our framework is robust to the loss coefficients. To intuitively understand the quality of the learning embeddings, we visualize the extractive feature with t-SNE, where circle represents the source videos and triangle represent the target videos. It is clear to show that the features from the ABG achieve tighter cluster compared with baselines. And in conclusion, the difference from the existing approaches which learn domain-invariant features, we construct a domain-agnostic classifier by leveraging the bipartite graph to combine similar sources and target features at the training and test time, which helps to reduce the exposure bias. And the proposed ABG is flexible and agnostic to the choice of frame aggregation and conditional alignment modules. We further validate the robustness of the framework by extending to a semi-supervised setting. The source code is available on GitHub, and please contact me with this email if you have any questions. And thanks all for your listening.